In the last talk, part 1, we have seen the concept of predictive distribution in statistics. And then we show the optimality of Bayesian predictive distribution, which is historically shown by H. 1975. And today, as a possible application of the concept of prediction to quantum information science, we will see an application to quantum state tomography. Quantum state tomography is a basic tool in quantum information science and quantum information experiments. And then we show the optimality of Bayesian estimate in this setting. Here are today's contents. We will see less than half. First, we briefly review the quantum state tomography. And this talk is not to physicists, but it's to statisticians. So we ignore detailed quantum theory or quantum information. Okay? And then we introduce the density matrices, which is a basic ingredient in quantum information. And we propose the method of predictive density matrix. And finally, we will consider how to evaluate a predictive density matrix. And we show that the optimality of Bayesian estimate in the quantum state tomography. Now let's see the brief review of quantum state tomography. So what's a quantum state tomography? Roughly speaking, it is a certain kind of parameter estimation from experimental data in quantum physics, especially in quantum information experiments. And it has now become a very basic task in many kinds of quantum information experiments. So you know the word quantum computation, quantum computer, and these tools are used in this exciting area. And quantum physicists, both theoretical and experimental, usually do not understand modern statistics. Typically, they do not know hypothesis testing, admissibility of estimator, complete cross-sum, and so on. But now, some people become interested in statistics, machine learning as a useful tool. Okay, let's see the brief history. Decades ago, some people recognized that a naive estimate, which is called a linear estimate, is problematic for a small set of data. This problem was called the negative eigenvalue problem. In order to solve this problem, Frodil, 1997, proposed a maximum likelihood estimate. And other people proposed a Bayes estimate. Another group proposed a least square estimate and used it in their own experiment. This is the history. And now let's see the problem. What's the problem? In a very simple situation, we will see this problem. Before details, we review of our notation. Please recall this. If we write x tilde bin n comma q, it implies x is distributed according to a binomial distribution of the number of trials n with success probability q. And we often more explicitly probability function. Okay, now let's go to the problem in quantum state tomography with small data. Okay, let's consider standard quantum state tomography of a single qubit. Statistically, it is a parameter estimation in a restricted parameter space. And a qubit is a unit of computer. And we prepare the qubit. And experimentally, we want to know what the qubit state is. And the single qubit is specified by a real three-dimensional vector. So from experimental data, we want to know each vector component. But it has a restriction. The norm of the vector is equal to or smaller than 1. This is a restriction on the parameter space. And statistical model is given by the following 3 binomial variables. Each W is distributed according to a binomial distribution. So we observe W1, W2, W3, and then we estimate theta 1, theta 2, theta 3. This is the most simple situation. And if we neglect the restriction, the problem reduces to a simple one. We only consider statistical estimate each binomial distribution. And then we can easily estimate by the linear estimator. In other words, okay, if we see the W, then Q is estimated by W by N. And changing to theta, theta is estimated by 2 times W over N minus 1 for each J. There's no problem. But if we consider the restriction, then it causes a certain trouble if we have small number of data. As an example, we consider very extreme case. Suppose that n equal 2, and we obtain W1 equal to, W2 equal to, and W3 equal 0. Then, the linear estimates are given by theta hat 1 equal 1, theta hat 2 equal 1, theta hat 3 equal 0. It is problematic because estimated vector is outside the parameter space. It causes a negative eigenvalue in density matrix. This is a problem, or this is the essence of problem in the most simple situation. We see that an estimated vector is outside the restricted parameter space. In such a situation, we usually adopt the following. Of course, this is very, very common sense in statistics, but it was something new to quantum physics around 2000. Okay, the first one is maximum likelihood estimate. In maximum likelihood estimate, we maximize the likelihood function in a restricted parameter space. So the maximizer as the maximum likelihood estimate always in a restricted parameter space. The second one is Bayesian estimate or Bayes estimate. This is, in a sense, the average in a restricted parameter space with respect to the posterior distribution. Okay, we briefly see the two definitions. The first one is maximum likelihood to estimate. For notational simplicity, from now on we often write the parameter x, y, and z instead of theta. Then, the likelihood function is explicitly written as follows. Here, W1, W2, and W3 are observations, and we maximize as a function of x, y, and z with a constraint x squared plus y squared plus z squared between 0 and 1. In a sense, we consider optimization in the unit sphere in a three-dimensional real Euclidean space. Then, we see the Bayes estimate. Please recall the last talk in part 1. In Bayesian statistics, we first set a prior distribution anyway, and here we set a prior distribution pi denoted by pi of x, y, and z over the sphere. And by definition, the density pi, the total integral of pi, is equal to 1 and non-negative. This is due to the definition of probability density. And anyway, after specifying a certain prior distribution, then automatically we obtain the posterior distribution. It is calculated by the formula, and here, using the likelihood function L, then we obtain the following form. Using the posterior distribution, we can construct so-called Bayes estimate, which is given by this form. This is, in a sense, average of each x, y, and z with respect to the posterior distribution. So we calculate the integral. And please note that the basic definition of Bayes estimate or Bayesian estimator, which is usually adopted by a mean of the posterior. Now let's see a certain difference between maximum likelihood estimate and Bayes estimate. In quantum-state tomography, the true parameter is often very close to the boundary of the parameter space, but not exactly on the boundary. This is a typical situation in quantum information experiments. However, maximum likelihood estimate as a maximizer often comes on the boundary of the parameter space, like this diagram. True parameter very near but not on the boundary. So we want to estimate the true parameter theta, and MLE often has a certain bias. Thus, Blumkoholt, in his article, he said the Bayes estimate is desirable in the above meaning. Now we see some of proposed methods in quantum state tomography. The linear estimator causes a certain problem for smaller data. And maximum likelihood to estimate becomes often on the boundary of the restricted parameter space. And Bayesian estimate seems so good in a practical situation of quantum state tomography. And around 2000, they had qualitative arguments for the above methods, and no theoretical argument anymore. Thus, here we reformulate this problem as a kind of prediction problem in a statistical framework in the next section.